Let's talk about waves a bit then. All waves of whatever type, light waves, sound waves, waves that run through a pendulum string, I don't care what it is, they're going to run into other waves. They have to. For example, a few minutes ago when I asked you guys to kind of all be quiet, there was a lot of noise around the room, right? Well, those are sound waves that are overlapping with each other. Does that make sense? And you get enough sound waves overlapping with each other and it gets kind of noisy in a spot. Whereas right now, it's just me talking, so maybe it's not quite as loud, but does that make sense? If we have everyone talking at about this level of loudness, those sound waves are overlapping to the point where it actually gets quite loud in the room. Okay? So pretty much waves will always interfere with each other. They're either going to interfere in a constructive manner or a destructive manner. I'm imagining that you guys know those words to some degree, constructive and destructive. Constructive would be to like build something up. Destructive would be to tear something down. So here I've got an example here. Imagine you've got some pulses sent through a spring. So imagine that you send a pulse, like a wave going this way, and a wave going this way. This diagram came out of your textbook, by the way. What's going to happen is these two pulses will overlap, and you're actually going to get like a combined pulse where it actually gets taller. And I've actually found an applet that works for this, and so I want to play with this applet for a little while here. So basically what this thing does is it's going to put a pulse on a string. And so if I just press a pulse button, it's going to send a wave back and forth, which is kind of cool. Now I'm going to send a second one. So what is happening when one of them is upside down and one of them is right side up? As they phase through each other, they cancel each other out. Is that constructive or destructive? Yeah, destructive interference. Does that make sense? Right at this moment right here, or right here, it's flat. Just for a second. If I could do this step by step for like a second there was no amplitude anymore. These waves would have canceled each other out. But then they continue on their merry way. Okay. Let me try this again. No, that's the same thing. I want to try to have them positively interfere with each other. No, that still didn't do it. What am I going to need to do to make that work? I'll do oscillate in a second. Pulse. Oh, it's going to cancel. I did it yesterday. Maybe I need to oscillate. Maybe let's try this. Yes, that's what I was doing. I was playing with this yesterday. Okay. Just need to mess around with this for a second. Bear with me. Let's reduce the frequency. Take down the amplitude. Restart. Okay. Play. Nope, still not what I want. Sorry, bear with me for a second. I'm going to make this work. I need to turn the frequency way down. That's what it was. Nope. More amplitude. Yeah, you can tell this is kind of fun to play with. I just can't make the point I want to make right now. I want to make them overlap with each other. There we go. Okay, now I got it to work there. I had to do it manually. So you guys see how I made this work here? It's not probably as nice as the last one, but as they're overlapping with each other, you see how they're getting taller? If that makes sense. And so here we're having constructive interference, where the amplitude is getting larger just for a brief moment of time. Does that make sense?
Yeah.
Okay, so one was constructive, one was destructive. What I'd like to do is just mess around with this one a little more. You can actually make what's called a standing wave, where you see how it's like working back again. This is kind of similar to resonance, where it continually seems to get larger and larger. I'll restart it. You see how it started off fairly low? And then as the wave comes back again, it's making it get even taller and taller. That's where the frequencies are starting to match, and the amplitude keeps increasing more and more and more. Kind of decreases again for a second, but wait, it'll pick back up again. And now it gets really tall as the frequencies start to match again. Kind of cool, eh?
Yeah.
So, no, I tried this last night. Hopefully I can make this work. The frequency was on. The frequency was on 30, I think. Nope, that wasn't it. It was on 10. Ideally, I'd like to give you guys a laptop and just let you play with this yourself, but I don't think it's going to work today. No? I'm trying to make something called a standing wave. There we go. I have it here. I just need to turn this off at just the right moment. Okay. Oh, it's close. Okay, this is not quite perfect, but it's not bad. This is called a standing wave. Come on in. Maybe. Okay. Do you see how this one's kind of unique in that there are some places that are just not moving? Hey, hey, come on in. Come on in. Emma, right? Yeah. Come on in, take a seat. Find somewhere to sit. Come join us. You guys all know Emma? Yeah. This is Emma. She's new, old. I don't know. You used to go here back in grade 9?
Yeah.
In grade 10 as well?
Formal, yeah.
Okay. Okay. Come on in. We're just talking waves right now. Do you guys see how, for the most part, those green balls in the middle there, they're not really moving at all? This is called a standing wave. And I want to bring back a couple definitions I've told you guys in the past. The very, very middle of the wave along the equilibrium line that doesn't move, we had a name for that. Do you guys remember what it was called? It's called a node.
Oh, yeah.
You remember that term there? Okay. And so those green balls, I guess, there for this wave here, those are called nodes. The very, very extremes then at the top or the bottom one, remember what those were called? Antinodes, yeah. So this is known as a standing wave. It's a particularly unique phenomenon where when a wave starts going out and then it reflects back and it reflects on itself, it actually like increases the amplitude and it basically looks like it's just going like up and down. When I think of this, I think of someone doing jump rope. I don't know whether you can kind of see the same thing there where, you know, like basically in the middle there, someone is doing jumping up in between there. Does that make sense? Okay. Just leave that running here. Let me go through some of my notes then, and hopefully the visual will help explain what I've got for notes here. So, some definitions I need you guys to know. Okay. The first definition is called superposition. Okay. If you superimpose something, do you guys know that word from like other contexts? It's like where you put something on top of something else. Usually when I think superimpose, I think like Photoshop. Where you like take someone's head and put it on somebody else's body, maybe that's superimposing. Okay. In a physics definition here, okay, this is a very wordy sort of definition. The displacement of the combined pulse at each point of interference will be the sum of the displacement of the individual pulses. Okay, that's really wordy. Here's the basic idea. If here is where one pulse would have been, and here is where the other pulse would have been.
Tasia Panzerbone, can you please come to the office?
This point right here is really this plus this. However high these 2 points are, this point just means add them together. However high this point right here is, would be this height plus this height. Right here, this curve has like no height to it. So therefore, these ones are both at the same point. Makes sense? Essentially, what I'm saying here is that blue plus purple, I know you guys don't have colors, equals red in the y direction. For those of you guys in my Math 30 class, we kind of did stuff like this in combining functions. I don't know whether that makes any sort of sense, but where like you add the y values to each other. Same thing's happening here with destructive interference. If you have a blue wave going upwards and a purple wave going downwards, really you just need to add up their values. So like for example right here, this blue value plus this purple value, since one's in the positives and one's in the negative, the actual wave itself will be right in the middle. Does that make sense? So that's called superpositioning, and the terms I need you guys to know are constructive and destructive interference. So basically, one makes waves bigger, one nullifies waves. Let me give you some examples of those that maybe you know of in real life. I already gave the example of constructive interference for that one bridge in Washington, where the wind was causing it to vibrate so much more and more that eventually that bridge like collapsed on itself. Destructive interference, we usually just call that interference. That would be like when you're trying to send different signals and they get blocked by each other because like they're canceling each other out. I gave the example last day, I think, of how my Apple TV and my microwave run on similar frequencies. And so when I'm running my microwave, my Apple TV just does not work. Because like there's just too many signals in the air at the same time and they cancel each other out. Brad.
How can light interfere with another?
What was that?
How can light interfere with another light?
Well, light ultimately is part of the electromagnetic spectrum. So you're suggesting light interfering with other light? Or light interfering with just other waves of generic types, like radio waves and microwaves and stuff? I don't know the answer to light with like say radio waves, but like radio waves with other radio waves, that causes a bit of a problem. Let me give you a different example here. In my van, I have, we don't have an MP3 player, so we bought one of those things where like you hook it into your iPod and it emits its own little mini frequency that then just your car can pick up on. Anybody else seen one of these sort of devices? Yeah. Where basically it's a mini FM transmitter. Some of you guys know what I'm talking about there? Okay. Well, those work really well on certain bandwidths. And so if you guys know the FM bandwidth, it basically goes from about 87, 88 up to about 107. That makes sense? And so like in Lethbridge actually has a couple of radio stations at the very top end of the bandwidth because there's 107.7 the river. And so if I try to set my little FM transmitter to 107, I actually get interference because the radio waves that I'm trying to send out from my little transmitter and the radio waves in the air from the river radio station, they're going to cancel each other out. Okay. So I actually send my little FM transmitter to about 88 or 89 because there are no radio waves being emitted at that frequency. Does that make sense? Okay. I'm sorry if that didn't answer your question, Brad. I'm not really sure how to put light into that. Because, I mean, light operates at its own wavelength. And so, like, red has its own wavelength, and blue has its own wavelengths. And so, like, those shouldn't I don't think those would interfere or with each other. I don't know. I have to look into that more. Okay. I'd like to show you guys a YouTube video. This is... I don't know if you've ever seen this before, but this is really, really cool. Just basically about how waves and pendulums work. Maybe I should stop that. It's still running. Let's try this YouTube video. Okay, so the basic idea here is he set up a whole bunch of bowling balls. All of them have a different length string of pendulum, and it creates basically a wave right here as it oscillates back and forth. Kind of similar to that one wave that I had on like the... I can't imagine how much setup time it would have taken to make this though. Like, this is crazy. Now, for a little while here, the wave basically doesn't really look like much anymore because it's completely... here's a term I want you to know. This is out of phase. Does that make sense if I use the term out of phase? Really, nothing is happening. It looks very scattered for a while. So you just think, oh, well, the experiment's done. Be patient. I think that's probably the, Oh, here we go. Hang on. This is the part where it starts to get cool again. Hang on. Be patient. We'll get there. Why there's noise? I think there's noise because ultimately these are on like pendulums, and I think they were probably held on like metal rods at the very top there. Here we go. Here's where it starts to work. Are they hitting that? Well, that would slow them down momentum-wise. I assumed it was based on like how like when I'm pushing kids in on a swing or something like that, that the actual like hinge at the very top is making some sort of squeak noise. But I don't know. Maybe I'm wrong. Yeah, I guess you're right. Yeah, they are hitting there. So I guess that's the reason why at the very, very end here, this wave actually completely goes right back in sync like when it started. It takes about 3 minutes, but then the wave actually restarts itself from scratch. But it's slightly out, and so that must be why, because there's like a little bit of friction lost every time it hits that. Bowling ball. Okay, start watching again here. I don't know if you guys can see, but it's starting to take a wave shape again all of a sudden. Where all of a sudden these bowling balls are coming back in phase. It's taken a while, but based on like their frequency patterns, they're finally starting to oscillate back in phase again. Well, okay, so this is back to about where they started, where they went like this. That's about where it started, and now it should start re-oscillating. It's not quite perfect, but as a bit of a wave again here. See how it's restarting that wave shape again? It's not quite as good as the first time around, but... Anyways. So basically the way that works there is they set up like, it must be like 30 different bowling balls, all of which have a slightly different pendulum length. And so like the one on one side goes like this quite quickly, whereas the one on this side takes a long time. And so since they all have a different length, they all have a different period, if that makes sense. And so when you start, like basically they all go together, but then like this one way over here has less distance to travel, so it can go back further. And then this one has longer distance to travel, so it takes a while to get back. And it starts to make that wave sort of pattern. Yeah, I'm sure you can find all sorts of other little mini versions that are made, but that one's kind of cool because it's like massive backyard bowling ball project. I will give you an A. Okay. Let me finish my notes here. I don't actually have that much left. Most of it's just reading here. Okay, a couple of things I need you guys to know. Just like with the bowling ball project here, a wave, when it exits, it's going to look the way it did when it started again. So hopefully these diagrams make sense. Here's one wave going this way, here's one wave going this way. For a brief moment, yeah, they're going to combine together. Okay. But when they're done, they're going to go back, like continue on their merry ways the way that they were planning on regardless. Does that make sense? Other notes I have here. If it hits a boundary, okay, you can actually reflect waves back and forth. Okay. Let me just pull open this guy here one more time just to make that point. That would be this simulator here. If I were to just send a pulse, need some amplitude. There. If I send a pulse, as soon as it hits this boundary over here, it will then reflect back the other way. Does that make sense? That's the principle behind like how, say, cell phones work. Your cell phone is sending out a signal to a cell tower, and it's immediately sending a signal back to your phone, and back, and back, and back, right? I mean, it's getting reflected off of one tower back to the other one again. If I were to go with no end, well, now it's not going to reflect anymore, and so if I were to send the pulse, it's gone. But if I throw a fixed end on, then it can actually reflect back again.
What's the loose end?
I don't know. Let's try it.
Oh.
So this one's a little different here. It actually sent it back the way it came, hey? So this one's a little different. I guess since this one didn't really reflect off of something, it actually just bounced and banked back the way it came from. Okay. Some more terminology I want you guys to know. I bolded a lot of words here. I need you to know what a reflected wave is. Hopefully that's pretty intuitive. It reflects off of something. Okay, so it'll just come back the way it came from. Okay. I gotta make a point here. The amplitude of the reflected wave, though, is going to depend on the density of the medium. A couple of terms here. What's a medium?
Something that we capture.
Okay, now when we're talking about like radio waves or some of those waves, they usually travel through air. If I go back to my simulator right here, I can increase what's called dampening right here. And so if I dampen this, do you see how it was trying to reflect, but after a while it lost the wave. Like here, I'm gonna send it, but does that make sense? The medium right here didn't really do a good job of allowing the wave to be transmitted all that well. Like, sure, the wave started, but it just kind of slowly died out. Another thing I can play with here is the tension in the rope. If I lower the amount of tension there is, it's a little bit different than if I were to increase the tension. It goes like a little bit of a faster speed. I send a new pulse there. So there's a fast pulse. And then if I lower the tension, wasn't really traveling as fast. So the point I want to make here is the actual thing that the wave travels through, it makes a bit of a difference. Okay, so if I were to increase the dampening all of a sudden, see how this wave right here is just starting to die out?
Everything's funnier in slow motion.
It's still moving though a little bit, right? Like you can still see it is moving. It's right about there now. No, I can see a little bit of wiggle.
Okay, you can still see it.
You guys still see a little bit of wiggle right there? Okay, fine, whatever. Okay, point I want to make here. Medium matters, okay? Whatever you're reflecting the wave through will make a difference, okay? The amplitude of the wave is how high that wave was. As I made the spring, as I changed its density and as I changed its dampening, you notice that the amplitude started to slow down a little bit. Good. Another term I want you to know is this one called a standing wave. A standing wave is where it just works out just perfectly that when this wave right here does this and this and this and this and this, it hits just perfectly right there. And then when it bounces back, it's like a mirror image. And you could keep this going ad nauseum, and then it hits here and it bounces back. And really, you don't get a whole bunch of combined overlap. It keeps going through this cycle. To here, bounce. To here, bounce. And it's like it's completely perfect with the other one. And it basically goes up, down, like that standing wave I made earlier. Does that make sense?
Well, that wave going forever then?
Yeah, basically, yeah. Because what's happening is it's basically reflecting, but in like such a perfect pattern that it really there is no, like there is interference, but like at this point right here it's perfectly constructive interference, and at these points right here you have perfectly destructive interference. Okay. I picked this diagram on purpose because I need to show you something. Let me just erase some stuff here. In terms of wavelength, why did that not erase? Erase. Okay. In terms of wavelength, do you see how all of these are labeled as half wavelength? Like 1/2 lambda? Okay. That's because a full wavelength would be here all the way up, down, and back to there. That would be a full wavelength. That makes sense? And so then from here to here is actually half of a wavelength. So if you're going to make this work properly, the distance from here to here has to be in an increment of half wavelengths. It could be 1 wavelength, it could be 2 wavelengths, it could be 3 wavelengths, but it also could be 7.5 wavelengths. A half wavelength would work just as well as a full wavelength. So like here is 1 wavelength, here is 2 wavelengths, here is 3 wavelengths. That would have worked. But what happens if I moved this distance right here, if I took this guy and I moved it back to about here? If I moved it to the right distance, an extra half wavelength would still have worked. Does that make sense? But what if I put the line right here? Then would it create a standing wave? Well then no, because it needs to basically hit right here at the node. It has to start at a node and end at a node, and then you can actually make a standing wave, which is kind of cool. Where does this get used? Musical instruments, actually. It's probably the most common place that we use standing waves. Okay. Let me give you an example here. Let's say you were to blow over the top of a bottle. It makes like a kind of sound on top of it. what's actually happening there is you are getting the air inside the bottle to oscillate. Okay? And it's actually creating a standing wave. Chances are, though, it's creating a very small standing wave right here. What ends up happening is at the top of the bottle, it actually has to be the open part of the wave, and at the bottom part of the bottle has to be a node. Okay? This actually is not even a half of a wavelength. It's actually a quarter of a wavelength. I'm going to try turning this sideways here. So here's a bottle. Okay? If you were to do this, that would be a full wavelength. Okay? And that might work, but usually what ends up happening is from here to just right here, you can actually create a quarter of a wavelength, where what ends up happening is it sends this down, bounces up, sends it down, bounces up, sends it down, bounces up. And as that resonates, it makes the pitch or the frequency that you hear when like a musical instrument gets played. Does that make sense? And so basically it just flutters back and forth. Okay. This is a really key thing here then. It's only a fourth of a normal wavelength. So I don't know that I can draw this really well, but basically here would be the up. Then you'd have to go back down. Then you'd have to go below and then back up again. And so from here to here, I'm not drawing this very nicely, to here, you actually need a quarter of a wavelength. You basically just need from the base to the top, and that's actually all you require. Okay, so let me show you some more pictures here. Any sort of closed column, any sort of instrument that basically has something on one end blocking it off, the requirements are you have to have a node of a wave at the very bottom for it to bounce. And then the top, you want to actually have an antinode. And so here is a quarter wavelength, which could be resonating as a sound. However, it's possible to put other wavelengths in there as well. So here is a quarter of a wavelength. This guy right here is actually 3/4 of a wavelength. Let me see if this makes sense. All the way up and back down, that's half a wavelength. All the way down to the bottom, if it were able to keep going right here, from here to here, that would have been a full wavelength. But if it was a full wavelength, it would be going from node to node. And we don't want that for musical instruments. We do want that for that standing wave, but for an instrument, we want to have the open section of the wave sitting right here. Does that concept make sense? Okay, let me see if I can draw this a little better here. Imagine I have an instrument that looks like this, and I want to send a wave in. Okay. Here's one way I could do it. If I'm blowing air in, I could send a wave in like this, have it bounce back out like this, and that would work. But that's actually a quarter of a wavelength. If I were to do a full wavelength, let me just try drawing this. A full wavelength might look like this. Up and down. Is that going to reflect properly? I'm going to say no, because I needed the node to be the place that exists there. So another way of doing this, though, would be to speed up the speed of this thing and go like, say, up, down, and then have it bank right there. Would that work? I'd say, sure, that would work, because then it could bank back up, back down, bank, and head like that. That would work. How many wavelengths have I drawn in green here, though? 1 1/4, yeah. From here to here is a half. From here to here is a whole wavelength. And then this is an extra quarter of a wavelength. Long story short, if it's an open on one side but closed on the other side pipe, it has to be involving quarters. So you could have 1/4, 3/4, 5/4, or 7/4 as your wavelengths. And those are the sort of wavelengths that would fit inside a pipe to make a noise. If you were talking an open column doesn't have something to bounce off of. So you don't want to go from node to node. You want to go antinode to antinode. And the way this would work then is you actually want half of a wavelength, because you want to start here, go down here. If you were able to keep going, that would be a full wavelength from here to here. But you don't actually want the whole thing in there. So half of a wavelength would work. Or you could even use a full wavelength. Like, for example, here to here would work. That's a full wavelength. Here to here would work. You could even speed it up. Let me try drawing a different one. You could go here, there, 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 and then this one would have to go there, 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 there. That would work as a wave inside of there making sound. That makes sense at all? Okay, so here's my point then. If you want to figure out what sort of pitch or frequency your instrument makes, it basically has to do with how many wavelengths can you fit in your instrument. Anybody here in band play the trombone? Okay, so could you describe to me how the trombone works basically? Okay, how does this thing work here? And what does that do though?
Well, the further you go out, the lower the tones work.
Okay, so the further you go out, the lower the tones work. Let me describe that to you. The further out you go means there's more length. The more length there is, the longer the wavelength. That make sense? So as you extend your trombone, there's more length to your instrument. Okay? The more length your instrument has, the longer the wavelength needs to be that fits inside of it. The longer the wavelength, though, the shorter the frequency. Is that right? Or is it longer the frequency?
What?
Longer the wavelength, longer the frequency?
Well, the pitch would be lower,
The
right?
pitch would be lower. Long story short, as you make it longer, it makes the pitch lower based on the fact that the wave inside of it has to be longer. Does that concept make sense? Okay, let me just give you the math example. This is the last one I have here. Let's say you have an instrument. Okay. The instrument is an organ column and it's 3.6 meters long. Okay. My question for you is, what is the frequency of this note? Like, what is the pitch of this note going to be based on this information? And the other piece I'm going to throw in here is you need to know the speed of sound. Okay, so 330 meters per second. Let's go with speed of sound. Let me draw real quick an open-ended organ column. So let's say we want to have sound resonate inside of here, and it's open-ended. The wave, could the wave look like this and be a quarter of a wavelength? If both sides are open?
Oh, if both sides are open, though.
Okay, so if this side is closed, you could do a quarter wavelength, but if both sides are open, then you need to have a half wavelength. Looking something like this. Okay. Which means that the actual wavelength is going to be twice as much as this distance here. So if this distance here is 3.6 meters, your actual wavelength is going to have to double. So your lambda is actually going to be 7.2 meters. Come on.
So then we just use lambda or velocity equals.
That's the formula, yeah. So then you use your formula. What is it? Velocity equals free frequency times wavelength? Okay. The wavelength that can fit inside your pipe, you can actually fit a half wavelength inside there. So then the full wavelength will be your distance times 2. So that'll be 7.2 meters. You're looking for the frequency, and the speed of sound was about 330 meters per second. So what's your frequency?
2,376.
Whoa.
No, you divide it.
You divide.
I was like, that's a really big number. 45.83.
45.83?
Seconds.
Well, it's actually hertz, right? With sig digs, yeah, 46. Okay, in terms of music here, I don't know if you guys know much about this, but if you have a low frequency, it means the note is quite low. The higher the frequency, it's a very high-pitched kind of shrilly type thing here. So this organ note must be playing a very low type of note. Does that make sense? Let me just do one more thing here. I'll just do one more example. Let's say that it was not a open-ended column, but it was a closed column. How would that change things? Well, rather than timesing this number by 2, you times it by 4, that's all. Okay? Which means that the frequency you have, like the wavelength you have, would actually be 4 times bigger. And if this number here was, rather than being 3.6, if it was, what would it be, 12, 13 or something like that? If your wavelength was increased, it would make your frequency even lower still in terms of hertz. Okay. Long story short, the longer the wavelength, the lower the note. Okay.